Yes, thanks again, Alan. I'm going to talk about a specific glacier in Svalbard that Alan and I have been studying. I've been studying it for quite a while, actually, which is Middelburg. The background to this is, again, probably things that we're all pretty familiar with, really. Why should we do this in the first place? Why glaciers are interesting things? Well, they're indicators of climate change, they're drivers of sea level change. Most of the world's glaciers have been, as far as we know, retreating for probably the last 100 years or so. What we want to know about them is, well, the details of how they change over time, mass balance, which is the difference between the annual input and output of ice. Obviously, if the glaciers in retreat, that is generally and to understand why they do what they're doing. Now, traditionally, the way to measure the mass balance of a glacier is quite pleasingly direct. In situ measurements involve hammering a load of metal stakes into the glacier surface and resurveying them year after year to see how they are carried down the glacier and how the level of ice varies as more snow is brought in and then as there is melting out. That's quite a labour-intensive way to go about things, and more modern methods of studying mass balance essentially use time series of digital elevation models acquired. Well, it's a number of ways of getting digital elevation models of a glacier. Air photography, stereophotography is the longest standing method, I guess. But nowadays we can also use interferometric synthetic aperture radar, INSAR. GPS, of course, is certainly accurate enough to do this now. You can do surface-based GPS survey, and LiDAR. LiDAR is what I'm going to mostly talk about. So the glacier that we're interested in is this one here. This is the Brøgge Peninsula, which is about 2/3 of the way up the left-hand side of the main island of Spitsbergen. You've got the map the normal way up. So Middelburg, as you see, is about 4 or 5 kilometres long. It's located just a few kilometres from the settlement of Ny-Ålesund, which is there. This is Ny-Ålesund, and that is Middelburg, so it's logistically quite convenient. It's not far from this place. It used to be a coal mining settlement. It's now a science settlement. It functions in many respects like a research base in Antarctica, and it's operating pretty much like that as well. So a lot of these buildings are in fact national research facilities. That one there, for example, is the British one. Those ones there are the Dutch station. That big grey one there is the Norwegian one, and I could go through various other countries. And the building you can't quite see there is a sort of central facilities building, which is run by, well, ultimately by the Norwegian state. So logistics and science happen here, and this is about 4 kilometres away from the glacier that I'm interested in studying. LiDAR stands for light detection and ranging, so it's, loosely speaking, it's the light equivalent and laser equivalent of a radar. So here's a cartoon of it happening. A laser pulse is transmitted, a very short pulse indeed, it's about a nanosecond long. It's reflected off whatever hard surface it meets, the ground, the ice surface, and the time difference tells you how far away it is from the LiDAR instrument to the ground surface. And if you know exactly where the aircraft was when it transmitted the pulse, you know where the pulse, where the reflection happened on the ground, so you know something about the geometry of the ground. LiDARs have been around for quite a long time now, decades. But I would say within the last decade, there's been a very rapid improvement in their technical capabilities, and they've suddenly become very interesting indeed. Well, let's say about five to 10 years ago, they became very interesting indeed. So it's an interesting time to be working with LiDAR data to explore the possibilities that it gives us for doing glaciology, well, other things too, of course. The instrument that we were using is called that. Optec is a Canadian company. The 33 part in its name means that it transmits 33,000 laser pulses per second. The typical configuration for this LiDAR is that it's flown about 1,000 meters, 1 to 1,500 meters maybe above the surface, and it operates in such a mode that it's capable of putting a spot down on the surface at roughly 1 meter, 2 meter intervals. It does this by scanning side to side and flying forwards and spraying this 33,000 spots per second down, so it puts a sort of zigzag array on the ground. The kind of accuracy that it can achieve, height accuracy, it depends a bit on the terrain that it's looking at, but it's typically 15 centimeters. To do this, you need to know where the aircraft is to an accuracy of some centimeters. So that puts actually very demanding requirement on the navigation of the aircraft. So it uses a lot of GPS basically. So that's the instrument. It's this box here. That is a LiDAR. It's mounted in this plane here, which actually the LiDAR belongs to this university, but the plane belongs to the UK Natural Environment Research Council, and they took it to Svalbard twice. Once in August 2003, and again in July 2005. There's the plane again. Yeah, that is the one. Operating from Longyearbyen, which is the capital city of Svalbard, and is about 60 kilometers or so from the glacier site itself. So the way you do this is, sorry, it's black and white. There's the glacier again. It's actually got a reasonably narrow swath. It scans side to side, but not over a particularly wide area. So the plane flew backwards and forwards. It did about 8 passes like this. That was it getting itself in the right place. And what's happening over there is there is a GPS base station. The one thing we need to do this externally is a GPS base station that can give you the correction data you need so that the GPS measurements are centimeter accuracy or better. So what you typically do is you set a GPS base station up over a point whose coordinates are already known, so a geodetic station. So that's a concrete pillar on a geodetic station, actually in the settlement of Nordsund, which is maybe, from the furthest point, maybe 10, 12 kilometers distant. So, what do we get? Well, as I said, the LiDAR was flown twice, first time in 2003, and what I've shown here is a slope-shaded representation of the surface that was generated. It looks so like an aerial photograph that I thought it as well to say that it isn't an aerial photograph. It's a slope-shaded representation of the digital elevation model we've got. I put some 100-meter interval contours on it just to help. But you can see glaciers there, very steep mountainous terrain, which is characteristic of Svalbard, is around the edges. There is moraine and forefields, and in fact there is the coast. And when we had that, we had the most accurate surface map of this glacier that anybody had ever seen. Because, as I said, it had a spatial resolution of around 2 meters and a height accuracy of 10 to 20 centimeters. And nobody had ever seen anything quite like that before, so we were pretty interested to see what we could see in it. And the answer was a lot. Many glaciological features. And this, and in fact the other one that we generated in 2005, we're now using a lot for, well, an increasing number of applications, but especially for surface energy balance.